Okay, so thanks, Ed. Thanks, everyone, for coming. Yeah, so this is on dimensionality reduction for scaling up kernel methods in machine learning. Oh, maybe maybe I'll just use this thing. Okay, so it's based roughly it's based on this paper we had in this past ICML called Random Fourier Features for Kernel Ridge Regression, Approximation Bound Statistical Guarantees. And there's a joint work with Chaim Avron, who's at Tel Aviv University, Michael Kapralov at EPFL, and then his student Amir Zandia and postdoc Amea, and then Cameron Musco is my brother also at MIT. And what we're going to talk about is studying sort of this class of Fourier methods for approximating kernel matrices from a matrix sampling point of view. And specifically, we're looking at methods proposed in this paper, this Random Fourier Features method by Rahimi and Recht from NIPS 2007. So that was the paper that this year at NIPS got a Test of Time Best Paper Award, and I guess the manifesto talk was about. So we're going to study that paper. We're going to reanalyze some of the methods in that paper using techniques based off what are known as leverage scores. And then I'm going to show you how, using these same techniques, it gives us an approach to sort of improving the methods in that paper and getting new Fourier-based kernel approximation algorithms that can give better approximation, ideally can give faster algorithms in practice. Okay, so there's a lot of open questions here. What I'm going to present is sort of just a starting point into reanalyzing these methods from a matrix approximation point of view. So at the end, I'll try to talk about what we would really like to solve, sort of the big asks on understanding these methods. Okay. So let's start with just a quick refresher on kernel methods. I think, actually, who has seen kernel methods? Yeah, I think everyone's seen kernel methods, but I'm going to do a full, just get us all on the same page so we all have the notation down. The idea behind kernel methods is I have some linear machine learning algorithm, like linear regression, support vector machines, principal component analysis, some algorithm that does function fitting or classification, but it either fits linear functions or it does classification or clustering by dividing points up with linear functions. And what I want to do with kernel methods is sort of revamp those algorithms so that they can learn nonlinear relationships. Kernel methods are sort of really widely used in machine learning because they're relatively theoretically understood. They can be applied to a lot of problems. And as far as methods for doing nonlinear function fitting or classification, they're relatively easy to understand.
But just before,
yeah.
Nonlinear, I mean, you can do using linear methods, you can do polynomial.
Yeah, so
by increasing the space. So this is called.
So this would include I would say this is nonlinear. So kernel methods will include that. We can increase the space to do. That's exactly what I'll show. So I could start with like a vector that has variables x1 through xd. And yeah, the only idea behind kernel methods is we just increase the space. So now I want to learn, instead of functions that depend linearly on the variables, if I wanted to learn functions that depend quadratically on the variables in my data vector x, I just increase the dimension of the data vector by throwing in all of the pairwise quadratic interactions between variables. So yeah, this includes things like fitting polynomials or doing class separation polynomials, but can also be much more general than that, depending on what features you add to the vector. So just to give the sort of the cartoon illustration, if we had some classification problem where we have two classes of points, and one class is distinguished by the fact that the points have smaller norm, we couldn't learn that class with a linear classifier because you can't write down a function that depends linearly on the variables and separates that inner core of points from the outer core of points. But as soon as we add on quadratic dependencies, we can learn a function of that type. Okay?
From a complexity theoretical aspect, you can view it as a reduction between learning problems where you reduce to the class of linear classifiers or half spaces, right? It's the same.
Yeah, exactly. It's the exact same thing.
The kernel is a reduction.
Yeah, the kernel's reduction itself. Yeah, exactly. Yep. So that's the simple example. The computational issue is that if we actually want to do this reduction explicitly, so say we're trying to learn functions of q-degree polynomials, we get massive blow up in the size of the feature vectors. So naively, we would get, if we start with d features, and then we want to do all q-degree monomials in the features, we get to d to the q dimensions. So computationally, this is a problem. It makes it almost impossible to run kernel methods with explicit feature expansion if we want to do any sort of high degree learning. So what the main idea behind how you do these things efficiently is we can often compute the dot product between the expanded up feature points, any two expanded up feature points, much, much more quickly than if we had explicitly expanded them and computed the dot product explicitly. And for a lot of learning methods, that's really all you need. If I can take my feature points and my data points, and if I can compute all of the pairwise dot products, that's enough to run the learning algorithm. So let's just do a really quick example, which would be linear regression. In linear regression, we start with some data matrix X, and our data points are x1 through xn. And we're trying to fit a function to match some response values b1 through bn.
So each of the x are the d-dimensional
Yeah,
vector?
d-dimensional vectors, exactly. And the way we would solve this problem, I mean, not thinking in kernel space yet, is we would want to solve like a least squares minimization problem, and I have L2 regularization here. So I want to minimize the 2 norm of x times w, where w is some parameter vector I'm going to choose, minus b. And then I have a penalty term on the norm of w itself. So that would be our standard least squares regression problem. And when I do prediction, w is now the coefficients of my linear function. I just predict by looking at my optimum, w star transpose times x nu, where x nu is some data point I get in. B nu would be, so I get some new data point in now. I get my linear function, which is represented by the coefficients in w star. And now if I get in a new data point x nu, and I want to predict b nu, my function value, I do the dot product. So we can equivalently just reparameterize this problem. So instead of solving for w star, I'm going to solve for a vector y star. And if the data matrix is full rank, I could write any w as x transpose times y for some other vector y. So I can just reparameterize the problem and minimize over those n-length vectors y instead of the d-length vectors w. And now you can see that solving this problem, it's a minimization problem that just involves the matrix x times x transpose, which you can write that matrix down if you can compute all of the pairwise dot products between points, between rows in X. Okay? So this is called the kernel matrix, and it's sort of the central object of kernel learning methods. We want to be able to perform operations quickly in that kernel matrix. So for the linear regression problem, what we would want to do is, what we would need to solve for the regulars problem is invert the kernel matrix with some sort of regularization added on. So you would need to compute the inverse of k plus lambda I, where I is the identity, to solve that linear regression problem. Okay? And we get the same picture if we had mapped x up to a higher dimensional space.
So n
Yeah.
we should think of as q to the d or something. If you wanted to learn a degree, whatever, k polynomial, then n would be d to the k. The original vector
Yeah.
of dimension d.
Well, so we're sort of just going to think about n as the number of data points we get in.
Yeah,
If you wanted to learn the
polynomial,
yeah, but you also have regularization added in. Yeah, so you should think of n generally as, yeah, larger than. Well, it sort of depends. Yeah, for polynomial.
You are trying to have the complexity sort of in a very almost non-dependent on n and dependent more on this. That's what. Like you don't want to write this k explicitly.
Yeah, that's what we're going to get to. So we're going to try to be faster than depending on n. Yeah.
So just to make sure what is loud and
Yeah, n should be, we should think of n as large, exactly. So for, yeah, not only if we're going to learn complex functions, n is going to somehow depend on the complexity of them. So yeah, we should still think of n as large. It was not more efficient than doing explicit feature expansion.
N here is
The number of data points, yeah. So this picture goes through if we're doing nonlinear dot products. So if instead of doing just regular dot products between ki and kj, we're doing it between those feature expanded vectors phi of xi and phi of xj. Okay? And as I said, often you can compute those dot products between the feature expanded vectors without doing explicit feature expansion. So this is a really simple example for the quadratic function we talked about. If I look at the value 1 plus dot product between x and y squared, it's not too hard to work through that. If you FOIL that out and look at all the terms, this equals up to some rescaling of the values in the feature expanded vector, the actual dot product between phi of x and phi of y.
Well, phi in this case is what?
So phi is the function that maps up your original feature vector to the higher dimensional space. So just the pairs, yeah, exactly. Yeah, all the quadratic pairs. So that's sort of how you would see, like if you saw this in an intro machine learning class, how they would justify kernel methods. But when people actually run these things, we sometimes forget about the exact mapping between feature expansion and kernel function. We just think of the kernel function as defining some sort of new similarity function as an alternative to the dot product. So the dot product, when two vectors get closer together, it increases in value. As two vectors get more orthogonal, it goes towards 0. You can think of the kernel function as just some alternative similarity function of this form. For 2 points that we consider more similar, it gets larger, and for 2 points that we consider less similar, it goes towards 0. So when you see people run kernel methods, they sort of just choose the kernel function independently about thinking explicitly about the feature map. So polynomial kernels are popular, but that second function I have up there, e to the negative xi minus xj squared, this is called the Gaussian kernel, which is very well used. It's a function that goes to 1 as xi and xj get really close to each other. So that's its sort of maximum closeness. It goes to 0 as they get far apart. Okay? There's a bunch of other kernels that have similar form. We have to pick a kernel function. Then we generally form this n by n kernel matrix, K. And we solve our problem by doing some operation on that kernel matrix. That's sort of the standard paradigm for kernel learning methods. OK. So the problem, which I think we're already picking up on, is that this can be super slow. So this is an n by n matrix. It depends quadratically on the number of data points. Even for reasonably small problems or reasonably sized problems, you're not going to feasibly be able to write down this matrix, let alone operate on it in memory, manipulate it to solve like your kernel regression problem. OK? So just writing it down takes n squared time. And then other operations take even more than that. Like inverting this matrix would naively take n cubed time, although you could use iterative methods where each iteration takes n squared time. But we just want to avoid, period, writing down this huge n by n matrix. And you basically need new methods. Then you can't scale these methods naively. The standard approach to dealing with this is to replace your kernel matrix by a low rank matrix. Okay? So we find that first off, in practice, we can typically get a good approximation for a dense n by n kernel matrix with rank much, much less than n. Often it's the case that if you're doing like a clustering problem where you have S clusters, sort of the rank of the approximation you get is about S. So these matrices are often low rank, and to speed up computation, we want to explicitly replace them with a low rank matrix. If you can do that with a matrix that has only S columns, you reduce your storage space to n times S, your runtime for like inversion to n times S squared. You basically speed up all operations in the kernel matrix.
So this is it's a standard approach, but is this the goal of, you need to pick a kernel.
Yeah.
Would this be the goal for which you would pick your kernel?
No, think of
having it as low rank as possible. Or this
no. I think you think about it as someone gives me some kernel ahead of time because they found it works on other problems, and then I will say, hopefully your kernel matrix is low rank. Computationally, we'll try to replace it with low rank matrix to speed up the algorithms.
They are not talking about the choice of kernel.
Not talking about the choice of kernels. That's given to us exactly.
That's based on expressivity.
Like what?
Expressivity, I mean, whether
No,
Yeah.
I just want to know whether the problem considers it. You can play with the kernel or you cannot play with the kernel. So you cannot.
One could try to do this too. Why not? Take the similarity metric and improve it by doing an operation on it so that the matrix K is directly to rank.
You could try to do this. Yeah, absolutely. But then you might be changing the expressivity of your model. It's hard to know how this will change, how it actually performs in the machine learning application. And there are some connections here, right? If I have my kernel function and this matrix is full rank, in some sense that's an indication that that function is too complex for my function, for the number of data points I have.
Isn't this equivalent to finding a low dimensional representation, like basically a low dimensional version of the embedding phi where you can explicitly compute the inner product?
Yeah, exactly. I'll write that down explicitly in the slides. But yeah, this is equivalent to finding a low representation embedding of phi. Yeah. Well, I'll show that in a minute, actually. What I wanted to mention is that we have very good low-rank approximation algorithms. They don't, your sort of standard low-rank approximation algorithms like iterative SVD methods, now we have very fast sketching methods, don't apply in this case, simply for the reason that they need to actually see the matrix you're low-rank approximating. So sort of the trouble here is that we're doing an implicit low-rank approximation. We want to skip forming K ever. We just want to go directly from data to the approximation Z times Z transpose.
There are papers by Kanan and later others which do low-rank approximation just by sampling.
Yeah, exactly. Yeah. I'll mention this. I'm going to mention this too, actually. So this is one way to do it where you avoid forming the whole kernel matrix K. And as Professor just mentioned, yeah, we can view this as trying to do some nonlinear feature map that's different than phi and much more compact, but still approximates that kernel dot product K of xy. So we're trying to take our data vector x, compute some nonlinear function of it to form some new data vector, such that if you look at f of xi transpose f of xj, this approximately equals K of xi xj.
Sorry, x in this is what? X is the data. I just want to.
Yeah, x is just still the original data point.
xi.
xi, yeah, xi.
Okay, so
X is the original data, xi,
something,
yeah.
So you want to compress even the data.
Yeah, you don't necessarily need to think of fx. I drew it that way. You don't need to think of fx as necessarily being smaller or larger than xi. Think of them as unrelated. We're going to choose the size of f of xi as we need to get a good approximation of the kernel matrix, but don't think of it as related to xi's size.
Okay.
Yeah.
Do you ever think of cases where some of the samples are outliers and you want to throw them away and improve this, or you always have to match everything?
I'm going to ask to match everything in getting a full low-rank approximation of this, but you certainly could ask for that.
And the low-rank approximation becomes much trickier if you're allowed to.
Yeah, if you can deal with outliers, exactly. Yeah, but it's certainly something you could ask.
But if you have something like a L2, you'll have an L2 error or something.
Yeah, yeah. So hopefully it's not an issue. And also, it's a Gaussian kernel. Even if you have huge outlier points, it only can mess up your matrix to some extent. All of the entries are bounded.
The rank could affect the rank quite a lot.
Yeah, it could affect. Yeah, it will be. We'll aim for things that depend on the error of the rank approximation. Yeah, yeah.
You said S could be more than D.
S could be more than D, exactly. It often will be because we're trying to represent. You can think of it as we're trying to embed that really high dimensional vector phi of x, which has much higher complexity than D. If it was q degree polynomials, that was a vector that initially had length d to the q, and S is an embedding of that, or f of x, which has S is an embedding of that vector. So yeah, I think don't commit to either way. When people run these things, sometimes it'll be more, sometimes it'll be less, but yeah.
ZZ transpose will be close to K, no?
Yeah, it would be close to K.
So then if S is more than D, why not taking eigentype decomposition of XX transpose and
Oh, because my mapping from X to K is nonlinear. It uses those nonlinear kernel inner products. So I can't, yeah, even if I could eigendecompose X, I don't get an eigendecomposition of K. Okay, so Avi just mentioned one of the standard ways of dealing with these problems of not having to compute x in full is doing sampling methods, which reconstruct a low-rank approximation by looking at subset of the columns or rows in the matrix, in the kernel matrix K. And when we do this sort of low-rank approximation, we only need to compute that subset of columns and rows, so we get a subquadratic running time. Okay? So there's been a lot of work on methods that work like this. One way of thinking about them is they're a nonlinear feature map from x to f of x. Is each entry in that map is some transformation of the distance between x, the kernel distance, between x and some other chosen landmark points in your data set. So it's sort of saying we can represent the kernel distances of all of the points in your data set by looking at their distances to some small number of points. It's like solving a noisy triangulation problem. If you believe your data lives in a low-dimensional space, it makes sense that you should be able to do something like this. Look at my distance only to some lower number of points to compute the distances between all of the data points. Okay?
Here the error will be in Frobenius now, right?
Yeah, it depends. You can get strong. So we have a recent paper actually that gets pretty strong. Yeah, you can measure it in a number of different ways. You can get, essentially, if you want to match the error of the best k-rank approximation in Frobenius norm, we now know how to do run these sampling methods where we take in total nk over epsilon samples. So this corresponds to k over epsilon rows and k over epsilon columns. And we can provably compete with the best Frobenius norm lower rank approximation without having to look at the whole kernel matrix K.
But it's a Frobenius norm error.
Yeah, it's a Frobenius norm error, absolutely. Yeah, you really can't. Yeah, exactly. Yeah. So Frobenius norm error is sort of, yeah, exactly. You could, like, spectral norm would be considered tighter, but we really don't know how to do anything like that unless we compute the whole kernel matrix. Okay.
So under some conditions or just?
Under no conditions, actually. So this is saying that it's a little surprising. It's saying I can do a low-rank approximation of this matrix by sampling rows and columns without looking at the whole matrix. The one condition that it uses is that that matrix is positive semi-definite. So the kernel matrix is positive semi-definite.
But the approximation optimal must be what, a Frobenius norm?
Yeah, and Frobenius norm.
Epsilon
Yeah.
times Frobenius.
So how is that?
Yeah, well, not times the total Frobenius norm of the matrix.
Sorry?
Not times the total Frobenius norm of the kernel matrix. Times the Frobenius norm of the error of the best rank K approximation.
Okay, yeah.
So if you had an exact rank K approximation, you could get perfect reconstruction. Yeah.
What was the Ravi Kanan's paper? What did he get? It was not. I remember.
So they did.
Or maybe there was a logarithmic factor or something.
So there's a couple things. One thing you can do is start with just doing, there's some sampling methods that are based on, okay, not in the kernel land, they're based on sampling by the norm of columns or rows.
Right.
If you do those, you get error that depends on epsilon times the whole Frobenius norm of the matrix. And so the big difference is we're only depending on epsilon times the Frobenius norm of the error of the best rank K approximation.
Okay, so it was
Yeah.
old Frobenius, right?
Yeah.
The older ones, yeah, were whole Frobenius, yeah. Yeah. There are ways of doing, for non-kernel matrices, there's ways of getting better error from those methods
But
using.
here it's NK sample, which they were working with K or something like that, right? Those are okay.
Yeah, well, I'm saying NK samples because I'm saying each column is size n, and then it's K columns.
Oh, so it is K.
So it is K columns, yeah, and
it's
K
not-
rows, yeah.
It's optimal, right? I mean,
Yeah, this is sort of optimal for sampling. Yeah. Okay, but we're actually we're not going to talk about sampling methods. We're going to talk about a totally different method, which I'll give you a sense of why, a method that's very, very popular in practice. I'll give you a sense of why people care about it. So we can do pretty well with sampling now, but in a little bit after I introduce the method, I'll give you a sense of why people care about doing it instead of sampling. So this is this random Fourier features method introduced by Rahimi and Recht. And they start with saying, okay, suppose our kernel function is shift invariant, which means that it can be represented as a function of just the difference between your two data vectors, x and y. So you can reparameterize this dot product instead of writing it as k of x comma y as just k of delta, where delta equals x minus y. So first off, this fits a lot of our standard kernels that people use in machine learning, like that Gaussian kernel, obviously, and then a bunch of other still popular but less standard kernels. Okay. We're going to mostly talk about the Gaussian kernel today. When we get into like the details later in the talk, we'll be thinking about the Gaussian kernel. So that you can think of as your prototypical shift invariant kernel. What they observed is, OK, if it's shift invariant, let's start by writing this kernel function k of delta using its inverse Fourier transform. So this is going to be a Fourier transform in d-dimensional space, because x minus y is a d-dimensional vector. So I can write k of delta as integral of eta is a frequency. So I'm integrating over all frequencies in Rd. And then p of eta is my inverse Fourier transform, e to negative I pi eta transpose delta. So I can write k of delta in that way.
You there or not?
Say again?
You there or not?
Yeah.
Yeah. It's just there or not?
Right. And the observation is just let's approximate this integral using a finite sum. So to approximate that kernel function, I mean, this isn't going to be giving me a lower rank approximation yet, but I could approximate it using a finite sum. So I'm going to take, instead of looking over all frequencies, just s sampled frequencies, eta 1 through eta s. And then that Cj is just some reweighting, because I'm going to have to weight up the importance, which I consider some frequencies, because I'm not going to look at all of them now. OK?
You would like to sample according to the Fourier coefficient. Yes. You would like to take the
This is ultimately what we will do. We will sample by the Fourier coefficients. Yeah. But like, we'll see some ways this is not the best thing to do.
Okay.
So the first observation, before we think about how we're going to do the sampling or do the reweighting, is that this immediately gives a lower rank approximation. It's a little different than what I was talking about before. Just note that here I'm factorizing my matrix as z times z star, where z star is the Hermitian transpose. So not only do I do the transpose, but I do the conjugate for all the imaginary numbers in that matrix. So if I factorize z times z star here, z has one row corresponding to each of my data points, x. And if I look at the value of all the entries in that row, I have one for each of my sampled frequencies. And now if I sort of look at the two rows from z and z star correspondingly and do their dot product, it's not too hard to see that it exactly equals that finite sum. So the dot product between this row in z and that row in z star, that column in z star, approximates as I desired my kernel function if my finite sum is a good approximation for the integral.
So
Yeah.
Is this implicitly assuming that the data points are uniform in RD?
No.
Like to get an approximation, approval approximation.
Oh, so this is, you'll see, you can get certain provable approximations from this with no assumptions. It sort of depends what sort of approximation you're going for.
No, but your kind of approximation.
Yeah, I'm saying no. I'm saying at least for their method, we don't assume anything about the data points in RD, and we can get an approximation out of it.
But you are assuming that for some s that's a good approximation. That's an assumption.
Yeah, that's an assumption. Yeah, sure, that's an assumption that we will be able to get a good. Yeah, yeah. But for now, we don't think about anything. Our data points can be arbitrary anywhere. In their paper, they give some better approximation bounds that assume the data points are bounded within some radius, but we're not even going to talk about those because I'm going to do something different than what the Reweighing method does. Okay.
So what are you assuming here? That the Fourier transform is.
I think the assumption is that the finite sum is a good approximation.
Yeah. I'm just assuming that. Yeah. I'm just saying. I'm assuming that finite sum is a good approximation. I haven't shown you why that's the case yet.
But wait, where's the data in that finite sum? Delta is what?
Delta is the difference between data vector x and data vector y. So I want to assume it's a good approximation for any pair of data vectors, x and y. So delta is x minus
So
y.
in the data distribution.
Yeah, yeah.
In principle, you could have better approximations if you knew more about delta.
Yeah, absolutely.
You're
So
not letting these constant CJs depend on delta at all, right?
yeah, it doesn't depend on delta at all.
Or even some kind of range where these delta.
Yeah, when we do, yeah, exactly. We don't depend on anything about the data.
If you do though, then you would not get low-rank approximations because then you would have used different frequencies for different data vectors.
Yeah, but you could imagine choosing some like optimal set of frequencies, optimal set of reweightings for your specific data set. But okay, yeah, I was,
You could
yeah.
partition the space of delta into depending upon some properties and then use different C's for different parts.
Yeah. So when I was saying that I was going to talk about the differences between these methods and the sampling methods, sort of the beauty of these methods is they're a method like this is totally data independent. So I'm going to choose those CJs, choose my samples and choose my weights independent of the data set. This seems strange, right? I should be doing an approximation that adapts to the data, but it's really nice when you're running these things in, say, distributed environments where I have different data vectors on different machines. If I can do things data independently, I can just compress those data vectors down in my nonlinear way independently across the machines. So it is actually,
It's not totally independent of the data.
It's not totally independent, yeah.
The Gaussian kernel or what.
yeah, it's not totally independent of the data. But it's, I guess the way to say it is data local.
Yeah.
Each compression only depends on one data vector. And this, we actually think about this as a desirable property.
Yeah.
So you can think of the sampling methods as really good if you're willing to adapt to the data. These just look at one data point at a time and compress it down. OK. So yeah, the question is how do we choose the frequencies and how do we choose the weights? And we're going to do exactly what, oh, well, yeah. First I should say this, but we're going to do exactly what Avi said. There's, by something called Bachner's theorem, if you have, OK, K has the property that it's a positive semi-definite matrix because I could have written it as a factorization of these feature expanded vectors phi x and phi y. So it has some factorization, so it is a positive semi-definite matrix. For all kernel functions that produce a positive semi-definite matrix, it turns out that the Fourier transform of the kernel function will be an all positive function. So just as a proof by example, we know that this is true for the Gaussian kernel. So the Fourier transform of the Gaussian function in high dimensions is just another high dimensional Gaussian. So it's going to be some all positive function. And this means that I can reweight that Fourier transform and use it as a sampling distribution.
Why do you need this example as a proof? I mean, it's a positive definite matrix, all its eigenvalues are non-negative, and being shift invariant, Fourier transform diagonalizes it. So this gives you that.
Oh, so this is, I guess this is the
Fourier
statement.
coefficients are eigenvalues.
Sure.
So they are all non-negative.
I think that's the
Yeah, I guess that's a proof of Bachner's theorem. Yeah, sure. Yeah. OK. So what we're going to do is, OK, P of eta, we're going to sample by, say I normalize it to be a distribution. We're just going to think about sampling frequencies according to that distribution. And I'm going to set all of my weights to be 1. And then it's not too hard to see that. So my finite sum is just going to be 1 over s times e to the negative I pi, eta j, that's my jth frequency I chose, transpose delta. And then it's not too hard to see that this expectation, at least of this finite sum, it's correct in expectation. So this equals the Fourier transform P of eta times the complex exponential. OK? Yeah.
Yeah, in the original paper, this, I mean, I haven't read the follow work. They were assuming that these rho n's are known, right?
Yes, they're assuming it's known because you have some sort of like some closed form value for it. Yeah. So I mean, yeah, you could. There are a lot of kernel functions where it might even be known but hard to sample by. So you're sort of assuming two things: it's known and it's easy to sample by.
Right.
Yeah, for Gaussian kernel, this is certainly true because it's just sampling from a high-dimensional Gaussian. But yeah, it certainly doesn't apply to all kernel. Yeah, all kernel functions.
It's always sample because these are expectations of something.
I don't know. Yeah, I don't know. You could imagine some crazy function where you had a closed form, but you have no way of sampling from it efficiently. OK, so the analysis in the original paper is really simple. So it says that I'm approximating that integral with a finite sum. And I want to see how well did I approximate all of my kernel dot products. All of the values in that finite sum have magnitude equal to 1, because they're complex exponentials. So they have real part equal less than 1. They have imaginary part less than 1. I can just apply a Chernoff bound sort of like independently to the real and imaginary parts, and say that if I took log n over epsilon squared samples, I'll preserve the dot product with probability like 1 times polynomial, or 1 over polynomial and n would be my failure probability. So that means that I can union bound over all of my n squared dot products. I preserve all of them with high probability. So all I need to do is take log n over epsilon squared samples, and I preserve that kernel dot product. OK? That's basically the analysis in the original paper. And once we had that analysis, this method sort of took off, because I just want to take 1 second to say how you would implement this. All it is you're taking your data matrix X. I'm sampling my frequencies by drawing them from a high-dimensional Gaussian distribution. So this is just building some random Gaussian matrix that I have on the right side there. I need to do those transpose my data vectors. So it's the same as multiplying my data matrix by random Gaussians. And then I apply sort of like a point-wise nonlinearity to all the entries in X times the random Gaussian matrix. So these methods there's like 2 lines of code to implement. And as I said, they're data local, so they're very easily distributed. And yeah, we already talked about it, but the term for this, the fact that I can compute this independently for every data vector, is called an oblivious sketch, as opposed to the data-dependent sketches, the Nystrom approximations. OK, so they work really well. They're widely implemented, these random Fourier features methods. The problem is that the only guarantee we just proved was that we preserved k entry-wise to additive error epsilon. So we approximated the matrix to plus or minus epsilon in every entry. And this doesn't really pass down to any interesting bounds on the matrix k itself, like looking at k as a matrix. So if you wanted to get bounds on, say, some norm, the difference between ZZ star and k, I would need to say in the worst case, all of these epsilons could correlate with each other. Epsilon E there is a huge matrix. So I need to set epsilon like on the order of 1 over n to get any sort of low rank approximation guarantee, which means I'm taking like n squared samples. I didn't do any compression.
So in terms of classification, is this bad? Or?
This is bad. Yeah, so I'll talk about it in a second.
This is the problem with the original paper too, right?
Yeah, exactly. Well, I mean, it's not clear it's a problem. So you can still run these things. They still pretty much work. But at least in terms of theoretical bounds, say you wanted to say you compete with the best low rank approximation, you can't say that in any way.
So
Yeah.
So this is a bit unfair, because even for the Nystrom method, right, you only compare to the best rank k. It could also be arbitrarily bad in each coordinate, right?
Yeah, this is true. So you could, it could be arbitrarily bad in each coordinate, but some things you can say. So if you can compete with the best low rank approximation, you can start saying downstream guarantees for things like how well does ZZ star plus lambda I inverse approximate k plus lambda I inverse. And you can say things like, if you took a number of samples that depended on something called the statistical dimension of the kernel matrix, which I'll introduce in a minute, you can actually get a good approximation of that inverse to the true kernel matrix inverse. So then your claim is, if I run the method with the low rank approximation instead of the true matrix, I could solve kernel ridge regression approximately. Yeah, so sort of we're trying to say we can get approximations that then pass down to the kernel ridge regression.
You might have a competitive approximation compared to the best some form of low rank matrix. Not low rank like Nystrom, but some other.
Sure. Yeah.
So the weakness of this is just that it's too general still, right? It's not only oblivious to the data, it's oblivious to the kernel. It uses only the shift invariance.
It uses the only shift invariance in the Fourier transform of the kernel.
Yeah, but it doesn't use what k was.
No, the sampling of it.
Well, the sampling is it samples by the frequencies by the value in the Fourier transform.
Okay.
So it does use the kernel, yeah. But like what we're trying to do is make these methods better without doing anything more. Like we're still trying to keep things as data oblivious as possible and only depend on the kernel function. Okay, yeah, but as I said, they're super fast. So what we're interested in understanding is, can we get more matrix type error bounds that then pass through to the downstream applications? Yeah.
If you knew that the pointwise approximations were completely independent, you would get, that's the best thing you could hope for, or you're expecting more than that?
So even if you knew they were completely independent, you're going to still need to take some number of samples that depends on n. It would just be a lower polynomial in n. I'm going to hope for something better. I'm going to hope that if you posited that the matrix was low rank, I could get a number of samples that depended on sort of its approximate low rank, its low rankness. Yeah. But that would certainly be good. That would be a starting point. You would get better bounds.
So what do you need for classification? Let's say there's a margin.
Yeah, so we're going to get to that in, yeah, 1 second. Where am I going to, oh.
So all this was
Oh,
not
yeah.
done, was it, in the original paper? Like, suppose you have a margin. That's
Well, they do have some things in the original paper where they do sort of, I can't remember exactly, but say if you had a smooth function and you're sampling, you're getting data points at random, they can get the error of the, you can get like your generalization error somehow competes with the generalization error you would have gotten for the regular kernel matrix.
Really?
There's some data-dependent assumptions. I'm not sure, actually. So they do have some sort of statistical, and there are people who've been very interested in saying, forget about the computation, forget about approximating the matrix. Can I prove statistical guarantees for these methods? Do they give the same statistical guarantees as the actual kernel method?
Assuming margin.
Assuming something. I don't know exactly where this, yeah.
Computational advantage in the original paper. You need to sample, you might as well execute the original.
No, because there's no sampling algorithm.
Right.
No, that's different. Assuming you have a
No.
sampling algorithm.
Even if you do sample, you need to sample so much.
Oh, is this true even for
Yeah.
statistical
You
guarantees?
said it, but, like, we need to
Yeah.
sample so much that it's like, just use the original matrix.
Yeah, I mean, that's why the Rahimi talk, the infamous one, cracked me up because.
Right.
Well, hopefully, maybe we're trying to fill in the gaps a little bit.
No.
Yeah.
So the matrix Chernoff bounds of Alfred the Winter and
I'll mention these. They will give,
yeah,
they're going to give something better.
okay, because they give you something with respect to the norm of the matrix.
Yeah, exactly.
It's not pointwise.
Exactly. So I'll mention this. So actually, before we talk, and I want to get to Sanjeev's question, but I realized it's a few slides later where I'll show you actually what sort of guarantees we want for the downstream learning. But before we do that, because we are going to start, the way we're going to understand how we approximate the matrix is by, instead of viewing this as approximating the integral, which is inherently tied to approximating all of the points in the matrix, we want to view this random Fourier features method as a matrix sampling process. So we can start applying things like matrix Chernoff bounds. So we can apply matrix Chernoff bounds, get a better handle on how to get matrix type approximation guarantees. So this is a really terrible abuse of notation, but I'm thinking of the kernel matrix K as factorized. I'm just going to draw that matrix phi. Its rows are indexed by my data points. The columns are indexed by all of RD. So I have a column corresponding to every possible frequency. They'll be weighted, I'm just using this as a nice picture to write the integral. Okay, so I can write the kernel matrix K as this matrix phi times this diagonal matrix P of eta times phi star. Okay, are we comfortable with that factorization? It looks like it makes sense.
Wait, what's the abuse? Now that you say there's an abuse, I'm not.
Infinite size.
Oh, just an infinite size matrix, but I'm just always going to draw it as a matrix because it's easier it's easier to carrying around the integrals everywhere. Yeah, and I'm also not going to write, I should have d eta scaling all the columns in the matrix. I'm not going to carry that around. Okay, so first off, let's think about just throwing that diagonal matrix, square rooting it, and putting half on the left and half on the right. Okay, so this is going to be our reweighted Fourier matrix phi bar. K is a factorization of phi bar times phi bar transpose, times phi bar star. Okay? What Rahimi rect is doing is it's sampling columns by P of eta. That is exactly the column norm of the column in this factorization of the kernel matrix K. It's a squared column norm because it's a, or it's proportional to the squared column norm. Actually, I'll have some scaling factor depending on number of data points n, but all the column norms will be proportional to P of eta. Yeah.
So this is like leverage score sampling. Generally, it's a good idea.
Yeah, but this is not leverage square sampling. So this is, that's exactly where I'm going to go. So this is column norm sampling, the standard Fourier features method. We're going to want to do something better, and then we're going to get to leverage square sampling.
Wait, why is it not leverage score?
So P eta is just proportional to the norm of those columns. Leverage score is more complex to compute. It would be a value that you need to compute for each column. Yeah, to do leverage score, it has an expression.
What was the notation for the eigenvalues then? On the previous slide.
The P of eta, the P of eta. The previous
No,
one.
Oh.
P of
Fourier
eta,
coefficient.
the
So why is it not leverage score? Here
So-
are the Fourier coefficients.
Yeah, exactly. But when I have a factorization of this matrix K as two matrices,
Yeah.
and each of these columns is just n complex exponentials. So think of all of those columns with the same 2 norm. And then when I move that P of n into the factors, I scale all of those columns which have the exact same 2 norm. So their norms are exactly, their 2 norm is exactly P of n. So what they're sampling by is exactly the column norms, which doesn't correspond to the leverage scores. To actually make it correspond to leverage scores, which I'm going to introduce in a minute for everyone else, you need to be doing some transformation of that vector over an inverse and doing the norm of that. Yeah. So naively, they're not the leverage scores. But as Avi was mentioning, you can start getting better bounds already just from viewing it as norm sampling instead of doing these entry-wise bounds if you apply standard sort of matrix concentration inequalities. So even for trying to get a better method, it's a better way to analyze the method. And I think this is even written down in a couple places. I think in one of Joel Tropp's surveys on matrix concentration bounds, he uses this as an example.
So this would already give some advantage in the original paper as compared to...
Absolutely, yeah. It would already give an advantage in the original paper, yeah. Although it's not changing the method. So I guess if it wasn't working in practice, it's not going to change anything. But yeah, at least theoretically, it gives an advantage. Yeah, exactly. OK, so and then as we're always one slide ahead, which is good. Norm sampling is generally not the optimal thing you want to do if you want to approximate a matrix by some subsampling of its factors. So specifically, we know that we can get much better theoretical bounds on approximating the matrix if we sample by the so-called column leverage scores of the matrix. So these go under different names. In theoretical computer science, they sort of first appeared under the name effective resistances, which are the leverage scores when you're specifically trying to sample from an adjacency matrix of a graph. So leverage scores, if you've heard of effective resistances and the problem of graph sparsification, these are the generalization of effective resistances to any matrix. Okay. So I'm going to write down the definition of leverage scores in a second, but I just want to give a sense of what approximation bounds they give. So specifically, you can use a regularized version of the leverage scores called the lambda ridge leverage scores to get approximation bounds of this form, where I have ZZ star plus lambda I spectrally bounded between, or I have k plus lambda I spectrally bounded by 1 minus epsilon ZZ star plus lambda I and 1 plus epsilon ZZ star plus lambda I. So this is sort of exactly what you want if you want to approximately solve ridge regression problems using ZZ star instead of k and say that you get a good approximate solution.
What should we think of lambda as?
Think of it as provided. So it's your regular.
Its magnitude relative to the top eigenvalue of k.
Yeah. So most people, okay. I think of it as just it's whatever someone said the regularization was, but it's usually something that depends on like square root of n.
The lambda.
The lambda.
It's more or less proportional to the norm of k.
Yeah, exactly. If under that would be true if it was random data, like.
Yeah.
So it's sort of hard. There's all sorts. When you start saying, oh, this is how you should choose lambda, you start having to make distributional assumptions on all this sort of stuff. So yeah,
What is the scale of Z now?
the number of columns in Z.
No, sorry, I mean like, so you're saying lambda is, think of it as square root n, so what's the scale of Z?
Yeah, well, actually, think of lambda as lambda. Let's not fix it to be square root of n because it could change. What Z, I'm going to mention the scale of Z in 1 second. So yeah, I already mentioned this. I guess I can approximate, if I can approximate the matrix in this strong positive semi-definite low ordering, I can approximate its inverse. You can also use bounds like this to get sort of downstream error approximation for k-means clustering, kernel PCA, other problems. I'm not going to go into those. So the question was, so how many columns of Z do I need to get an approximation of that type? How many samples do I need to take? If I sampled by these ridge leverage scores instead of the column norms, I can take a number of samples that depends on the statistical dimension of the kernel matrix, which is this quantity. It depends on lambda, so I'm denoting that S lambda, the number of samples I need to get that guarantee for lambda. It's this quantity trace of k times k plus lambda I inverse, which is equal to the sum of, I look at all the singular values of k, and I sum over the singular value divided by the singular value of k plus lambda. So
Did you define what is the leverage score? I don't see it.
I'm going to define it on the next slide. Yeah, I'll define it. I didn't define it yet.
It's a different weighting of the columns.
It's a different weighting of the columns. We're going to sample.
That's what it will give before we know it.
Yeah, I'm just trying to give what it will give first. Yeah.
So if lambda is about square root of n, then the error you have in spectral norm is about epsilon square root of n.
Yeah.
Which is also what I guess you would get if the error matrix was assumed to be random signed epsilon weighted matrix, right?
Yeah.
So that sort of is like what Zev suggested.
Yeah, so you can sort of, at least in the square root of n, and I think that's what you get by just doing the column norm, analyzing the column norm sampling with matrix turnoff bounds. So yeah, but we're sort of not, so that's, exactly. That's a good way to think about it though. If you could sample as leverage scores, you're sort of getting yourself in that best case scenario. Yeah, but think of lambda as a parameter that could change significantly. So what this corresponds to is, okay, if I have a singular value that's greater than lambda, this is a quantity the quantity in that sum is between 1 and 1/2. So this value, the statistical dimension, is sort of like the number of singular values greater than lambda, and then some term that depends on the sum of all of the tail singular values divided by lambda. So if I did an optimal low rank approximation, I could get that guarantee by just using the number of singular values greater than lambda. So now I have that plus some part that depends on the tail. So in a sense, that's how we're competing with the best rank K approximation in terms of size. Okay? Okay, so now let's look at the definition of ridge leverage scores. Instead of just looking at the 2 norm of phi bar of eta times phi bar of eta star times phi bar of eta, that would be the squared 2 norm of phi bar of eta, I instead do that quadratic form over k plus lambda I inverse. Okay? That gives me this ridge leverage score, which I denote tau of lambda of eta. Okay, there's 2 problems here. First off, we can't compute those ridge leverage scores because they require building the kernel matrix and inverting it. But even so, even if we could compute it, the leverage scores for this factorization of the kernel matrix could just be some crazy distribution that now we're asking to sample by. We have this is an infinitely, there's infinitely many frequencies. It's a distribution with infinite support. We don't actually have a way of sampling by it.
But is it clear why it's better or why it's good?
Why it's good if we could sample by it?
Why should you replace the unweighted Fourier by this weight?
Because you would get guarantees like the first line on the slide. Because you get downstream guarantees for something like kernel ridge regression that competes with the best low rank approximation. Yeah. Okay, so we're not going to try to compute leverage scores. You could imagine, I don't know, doing some sort of MCMC method to sample from this distribution, but we're going to forget about that. What the goal of our paper is can we just approximate that distribution by some simple to represent the leverage score distribution, by some simple to represent distribution that at least upper bounds it. So if we sample by the probabilities in our simple to represent distribution, tau lambda of tilde, we only get oversamples of the columns. So that means we'll still get the very strong approximation guarantees, but this is something that's actually feasible to sample by, and hopefully we can do quickly. So the better we match the leverage score distribution, the better our approximation will be.
But
Yeah, go ahead.
it's obvious that if you oversample, you get at least as good an approximation. You have to pick the summary. You have to know by how much you overshot. No?
So it's actually not, okay, if you oversample and then reweight by, so you always will do a procedure where you sample by probability p and then reweight what you select by 1 over p. It's not too hard, it's not hard to show that oversampling is okay. As long as I always choose my probabilities higher, I'll do better. Yeah. The analysis of these leverage scores also comes out, it's just matrix Chernoff bound with some sort of transformation in it, and then you can see it from that. Yeah, so the more closely match this distribution, the better. Another way of viewing the bound I brought up with columnar sampling about analyzing it with matrix Chernoff is you could overestimate this leverage score distribution by just scaling up the Rahimi-Recht sampling distribution, which was the density of the Fourier transform, and taking your samples from that distribution. And this gives another way of sort of getting similar bounds to what we get from doing matrix Chernoff from Rahimi-Recht. So immediately you can show that we can get those strong spectral guarantees with parameter lambda with n over lambda times 1 over epsilon squared, even if we don't modify the Rahimi-Recht sampling distribution at all. But we're going to try to do better than that.
So, and that you will get with infinity component-wise?
You will get that approximation guarantee that was like ZZ star spectrally plus lambda I spectrally bounded around k plus lambda I. Is that what you mean?
But the result of Recht was component-wise.
Oh yeah, but I showed somewhere in the middle. I showed this other result where I said you could get bound on the actual 2 norm of the matrix k, the matrix norm of k and ZZ star, by viewing it as column norm sampling. But yeah, the original Rahimi-Recht was elementary-wise. Yeah, but you can get these matrix-wise bounds if you take this many number of samples and just don't change the sampling distribution at all. Okay, so we're going to try to do better than this. And the way we do that is I'm going to introduce a different characterization of these leverage scores, which first off will be our main tool for bounding them, but will also give you a sense of intuitively why there's something good to sample by. Okay, so this is the characterization. The leverage score of frequency eta is the solution of this minimization problem. I take my matrix phi bar, which was my factor of k, and I want to produce some vector y that recombines columns in phi bar to get as close to phi bar of eta as possible. So I'm talking about the leverage score for this column corresponding to frequency eta. I'm trying to find the vector y that reproduces that column from all of the other columns in the matrix. And the quality of my vector y is a sum of 2 terms. I want to get as close as possible to the true column. So I have that term depending on phi bar of times y minus phi bar of eta. That's saying how close did I get to reconstructing the column phi bar of eta. And then I have a second term that just depends on the 2 norm of y.
You could have taken the unit vector of this column, right?
Exactly. So you could have taken the unit vector of this column. You would have gotten the first term to 0 exactly, and then you would have gotten norm of y. And then this corresponds to column norm sampling. Because now your leverage score is exactly the norm of that column. Yeah, exactly. Good observation. So this optimization problem makes sense. It's saying if a column in that matrix is easy to reconstruct by other columns, so I can recombine those columns with a low weight, a vector y that has low 2 norm, then that column is somehow less unique in the data matrix, so I can sample it with lower probability. If the column's hard to reconstruct with other columns, it's more important to sample, I want to take it. So this is sort of the intuition behind why leverage scores are good sampling probabilities to get these very strong matrix type approximation bounds. Okay? But it's also going to be how we bound leverage scores by some closed form simple distribution. In particular, what we want to try to do is we're going to produce some candidate for y tilde, some closed form solution for this vector, and use it to get a better bound on the leverage score than we would have gotten by with the column norm. So specifically than we would have gotten by just using y tilde equal to the unit vector. Okay. So just to note, maybe this is really clear, when I'm talking about forming the product of phi bar times y to reproduce that vector, this is exactly, I could factor that weight matrix out of phi bar. This is just a Fourier matrix where all of my columns represent frequencies. So when I do this operation, it's the same as taking the Fourier transform of p to the 1/2 times y. That's a vector. There's just the same, think of it as a function. That's just the same as doing the Fourier transform of that function and evaluating it at our data points x1 through xn. Okay? So to understand how to form certificates of upper bounds on the leverage scores, it's a question of, can I produce functions whose Fourier transform is close to that column vector whose Fourier transform looks like the pure frequency on my data points? Okay? So just to sort of vastly simplify things for the remainder of the talk, we're only going to think about one dimension for now. So my data points lying in one dimension, just on a line. And we're also going to assume that our data points are all bounded within between negative delta and delta for some values delta. Okay? And what I'm going to do is, instead of trying to approximate the Fourier transform only at my data points, so instead of trying to have my Fourier transform approximate the pure frequency just at those marked out black points, I'm going to try for something harder, which is going to give me a less optimal bound, but we can at least, it's easier to think about. I'm going to try to approximate the pure frequency on the entire range negative delta to delta. Okay? So that's the quantity we need to bound. This is what our first attempt is. We're trying to find some function whose Fourier transform matches the pure frequency between negative delta and delta. Sort of the most naive thing to do here is make your function square root of p times y tilde be a sinc function centered at our target frequency. So if we make the function just a Dirac delta at the target frequency, I'll produce that sinusoid over the entire space. But I only want to reconstruct it between negative delta and delta. I only have to reconstruct it there.
You don't mind that it will blow up outside this range?
I don't care. I'm just saying I'm only going to do it between negative delta and delta. Yeah. And it will blow up outside. Yeah. So
it would be really low degree.
Yeah, exactly. So it sort of has to. So I'm going to approximate. So now, I mean, Dirac delta, if I actually, it's sort of ill-defined, but if I had to take the 2 norm of that, this would correspond to a 2 norm of like infinity. What we can do is, since we only need to approximate over that range, I want to multiply that function by a box function. This corresponds to convolving my Fourier transform, the Dirac delta, with the Fourier transform of the box, which was a sinc function. And specifically, it's a sinc function with delta. That has the property that I'll still reconstruct my function between negative delta and delta, but it will have much lower norm. And specifically, okay, we'll get the reconstruction exactly if we do this. And the size, the 2 norm of square root of p times y tilde, will be on the order of delta, okay? Which we consider a good bound, actually, on the ridge leverage scores. The reason being is that, I'm going to get into this in a second, if I do have a range of, if I have data points on a range of negative delta to delta, I can choose my data points. At least there's some adversarial set of data points that will have statistical dimension about delta. So if we can bound every leverage score by delta, this would be good. The problem is that, okay, actually all I did here was bound the 2 norm of square root of p times y. The 2 norm of y itself, which is what appears in our function for the leverage score, is actually much larger. Because, to back out y from square root of p times y, we need to multiply by 1 over the square root of p times y. This is 1 over the density of a Gaussian, which grows actually super fast. It certainly grows much faster. The sinc's falling off, but it grows much faster than the sinc falls off. So I don't get a good 2 norm bound on the vector y itself. So what we end up doing, I'm not going to do the math gets a little gory, what we end up doing is instead of approximating just by that sinc function, we dampen everything by a Gaussian. So we multiply our test function on the right by a Gaussian, which corresponds to convolving that box function with a narrow Gaussian. And if you set your parameters right, you can do this in such a way such that my error on approximation on this function is not too large, and I can actually bound the 2 norm of y by order delta. Okay, so we're just doing some sort of dampening there to avoid that blow up on the edges of y. Okay, we can do this as long as there's some details in setting parameters. We can do it as long as eta is not too large. Sort of the takeaway is that we get a distribution that for frequencies that are bounded less than square root of log n over lambda, we just cap the leverage score at delta. And for far off frequencies, we use the Rahimi-Rek distribution scaled up. So we sort of get a distribution that looks like our original Rahimi-Rek distribution, but it's capped for low frequencies. Okay? And in total, we require something like order delta times square root of n over lambda samples to get the approximation guarantees we cared about, which, at least for some adversarial set of points, about matches the statistical dimension. So about matches the optimal that you could have gotten from, say, a nice round approximation or an actual singular value decomposition. But it's certainly not like an instance-wise optimal bound. It just could match for an adversarial set of points. Yeah?
Again, what was the assumption about the original kernel K for which this works?
So okay, we only proved for the Gaussian kernel. I think the statement would be that your kernel needs to have some sort of like bounds on how fast the tails fall off. Yeah.
I didn't understand the Gaussian filter. Can you write down what you would like ideally for this filter by doing the Fourier transform of your objective function and putting a filter and then seeing what's the optimal filter, or is just Gaussian? It seems to be the right thing to do by some equation.
You could do a better filter. So we just use the Gaussian filter because it's really simple to do. I need to bound those 2 terms. I'm trying to kill off tails, which means I want my Gaussian Fourier space to fall off fast. But I want to make when I do this convolution, I don't want to make too much error on the approximation, which means I want that Gaussian to be skinny. So there's a balance between the width of this Gaussian, and then it's easy to trade off because I can write down closed form expressions and optimize for the width of the Gaussian. But there are like better filter functions that have both small support and fall off fast. And
you could write down the optimal kernel by doing Perceval and writing everything in Fourier and then defining the optimal filter by the ratio of something or something else?
oh, maybe. Then it'd be data dependent, I guess.
Yeah. Just to at least have a target. And then
Yeah. I guess you could do this. Yeah. But what I'm saying is there's even better, if I just made the assumptions on the bounds of the data points, there's even better filter functions I can get there. But yeah, for sure. So Gaussian is just sort of a simple, it's just because it makes the analysis simpler.
You don't even know what would be the number of samples if it was the Laplace kernel.
Yeah, I don't know. I don't even know what sort of the worst case statistical dimension would be there. Yeah, I'm not sure.
Okay.
Yeah. I mean, this is natural. These are natural next questions. Okay, so we only have a few minutes left. I want to give a sense of sort of what happened. So this is, okay, what I have here. So why does this distribution actually do something different than Rahimi-Rek? This is the Gaussian kernel for 2 clusters of data points, where lighter values in that matrix represent values that are closer to 1. So I have my first data points in one cluster, second data points in another. The clusters are close, they have values close to 1, but the clusters are separated, so off diagonal I get zeros, okay? If we look at the error of what this sort of capped off distribution gives instead of standard Rahimi-Rek, is it concentrates error. This is a standard Rahimi-Rek error, which is darker on the diagonal. So it does a very good job.
Dark is good.
Dark is highly approximate. So this means it's sort of wasted approximation on the clusters themselves, which corresponds with large eigenvalues in the kernel matrix. Intuitively, for getting an approximation like this, that's not something I want to do, because I have these multiplicative 1 minus epsilon, 1 plus epsilon error terms. I'm allowed to err more on large eigenvalues of the kernel matrix. So I shouldn't have concentrated accuracy on those blocks. And that's sort of exactly what this modified distribution does. The error is worse on the blocks, but that means that overall it's somehow pushing its approximation to other parts of the matrix where it's more worthwhile. What we were sort of surprised to see is that if you use this distribution in place of Rahimi rect, you actually get better approximation in downstream function fitting tasks. I mean, maybe we shouldn't be surprised, but this was the goal, and it actually works out. So here's a function that we took a bunch, like a sort of an artificial sinusoid. We took a bunch of samples with random noise added and fit it with a true kernel ridge regression estimator, and we much more closely match that true kernel ridge regression estimator with this truncated distribution. And you do much better, for example, on the far ends of the function approximation than the classical random Fourier features sampling distribution. Okay, so already in low dimensions, there does seem to be actual gains in terms of function fitting from moving to this sort of more adaptive, more intelligently chosen distribution. And we see this in 2 dimensions as well. I'm not going to spend any time on that slide because I just want to take a second to talk about what I think the big open questions are. So we didn't try it for any classification problems. We really have only tested it for these sort of simple problems. Testing it and sort of understanding how it actually, when it actually does better is a really interesting question. Something we should do next. It should be better. Okay, like the reason I was surprised it was better is you chose your kernel function arbitrarily in the first place. So sure, we do better at approximating the kernel matrix K, but I don't yet have a satisfying answer of why. So you could think of Rahimi rect as just approximating some different kernel matrix. It's not totally clear, except for this idea of maybe putting too closely approximating in cluster instead of outer cluster variance. I don't have a great answer to why actually approximating that kernel matrix is exactly what you needed to do well in downstream tasks. Yeah, so there's sort of like a mismatch there. We do better in matching the output of kernel ridge regression, but it's not clear why we should do better statistically. You could do this, yeah. That's true. Yeah, that's true. Yeah, absolutely. So the big question here is, okay, first off, everything we were talking about is in low dimensions. We can do things in high dimensions, but you start paying like exponential dependence on log of the dimension, so you get really bad bounds in high dimensions. I think you can get, my conjecture is that we should be able to get oblivious methods like this with different sampling distributions that match the statistical dimension. So do as well as like a nice round approximation, and then in turn compete with the best low rank approximation. And maybe if anyone's interested in it, we can just talk about it offline. But there's something I'm working on is there's another way of viewing these leverage scores, sort of a dual optimization problem, where you can say that the leverage score is bounded as long as you can sort of bound the spikiness of any n sparse Fourier function. When I say n sparse Fourier function, this is like a continuous Fourier function. So I'm not choosing my frequencies from a grid, I'm choosing them from continuous space. There's already work on bounding these functions, their spikiness, in low dimensions. At least from my experiments and sort of intuitively, I don't see that they should blow up their spikiness. I'm being really unprecise here, should grow exponentially or in the dimension or anything like that. So my hope is that by bringing in more powerful tools than just the sort of test function design, we should be able to get much better bounds in high dimensions. And then sort of just as I alluded to in my answer to Elad, the other question that I think would be really nice to understand is, besides artificial examples, exactly why are we doing better in the experiments? Again, it makes sense computationally to target the exact kernel function, but it was pretty arbitrary how we chose that kernel function, how we chose our regularization to begin with. So I was surprised that we did better in function approximation and would like to understand that more. Okay, thanks.